Hi, my name is Brumfield, and I will be doing the lead for the jet engine experiment. And I know last week the last group wasn't able to do it, but I'm under the impression that his back has been repaired, and I'm kind of excited to get to do this one. As a little introduction, there are many uses for the turbine engines. Some good examples in power generation, where they'll burn natural gas and connect it to a electric generator to produce electricity. They're also used in helicopters, and they're called turbo shaft. And instead of having the exhaust gas to produce thrust, the turbine shaft is connected to a gearbox to be reduced, and then it powers the propellers. And the one we have is a jet engine, and they're used to produce thrust from the escaping exhaust gases. And they're used because they have excellent thrust to weight ratios, and they're highly used in airplanes. Here's a diagram of the experiment, and if you follow the white line, you can see the flow of the fluid. Notice the fluid enters from the left, it goes through the compressor, and it continues on into the combustor, where it's burned and through the turbine and out the nozzle to produce thrust. And you can see that we have many of the temperature and pressure sensors scattered throughout to collect data. Okay, and we'll be looking at the efficiency of the turbine. The efficiency is defined as thrust to fuel consumption ratio, and we want to increase the pressure ratio, which is defined as the compressor exit pressure versus the ambient pressure. To increase efficiency, we also like to decrease the specific fuel consumption rate and also increase the specific thrust, which is highly dependent on the temperature entering the compressor. So ultimately, we want high pressure and high temperature gases entering the turbine, but this puts a lot of stress on the material, so we need high quality components such as nickels, superalloy nickels. So the objective is to perform a thermodynamic analysis of the jet engine, review the Brayton cycle, and quantify engine performance. This is a temperature entropy diagram of the cycle. Notice that the solid lines are theoretical, the dashed lines are going to be more of your actual results. And you'll notice that the combustion and the nozzle work at constant pressure. And here are the equations. First, start off with the first law. So you have your mass flow rate and entropy coming in plus your fuel added is equal to your mass flow rate out times your entropy and your velocity. So to calculate thrust, it's just simply velocity over thrust over the mass flow rate. And to check the results, we want to make sure that the work at the turbine is relatively close to the work through the compressor. And here's your fuel calibration rates. These are data points from the company who produced the turbine. And I went ahead and put in a linear and an exponential graph. I believe the exponential is marginally better than linear at defining the points. And also this fuel rate versus the millivolts. And this is much closer. You can see the difference is much greater between linear and exponential graphs. And here's another point. I was told to calculate the exhaust velocity versus RPM. If you notice, for the first 2 points, they stay relatively closely, but when you calculate the velocity with the pressure, it's more of a linear, but then the thrust it spreads out and it goes away from, it starts separating a lot more, and it's not quite as accurate. Some of the causes of errors is In the combustion, we'll note that in the calculations, we're assuming that all the combustion occurs in the combustor, which is not true for turbines. It'll actually continue to combust all the way through the turbine and even out the exhaust. And even some of the sensors, some of them could be placed in bad spots. There could be hot spots in the turbine or small high pressure regions, which can cause error in our results. And also in the calculations, I use the specific heat of air, and which is not entirely accurate. It could actually be slightly different, considering that it's not only just air, it's air and fuel, and that can cause some errors in the results. Are there any questions? Marcus?
I got a simple question. How does the turbine engine start? Is it similar to how automotive engines start?
Roughly. They have to spin up the turbine, get the pressure going, and then usually you can, some people have like a small air nozzle going in, and that'll help spin up the turbine. Once it gets to speed, then the expanding gases will take over and continue to power it.
So it's not like an electrical automotive or anything? Or
Some
it just depends?
big jets have that, yeah.
You know what was wrong with one in there?
I have no idea. I just told it was broken. I'm just glad it's back. Any more questions?